I am bringing you today a little short video to talk about my favorite structure for activities. The reason that I really love this structure is that it gives an opportunity to really help students get to conceptual understanding and allows you as a teacher to see really what do kids know about a topic. So obviously this activity structure is called always, sometimes, never, true, and involves students analyzing statements that are made and determining which category that statement fits in. Is the statement always true, sometimes true, or never true? So I love this activity so much that I actually have 4 different versions of it. And I love the fact that it's very versatile. So it doesn't really matter what the content is. If you can create statements, mathematical statements about that topic, then you can create this activity. And it doesn't take really long. It doesn't have to involve a lot of resources. And certainly you don't even have to have it in print. So I'm going to show it to you today, just using a PowerPoint slide and some of the cards from one of my activities that I clipped out and put in the slide. But you could put your statements on sticky notes and have your kids put them on a location in the board where you designated parts of the board to be where always, sometimes, or never true statements would go. You can do it on their desk. They can just write those 3 columns on their desk using dry erase markers, and you can, manipulate the cards or statements. You could have them write them down because you posted them on your overhead projector. You can do it card based, which is how I do it, any way that you want. So this particular one is focusing on the concepts of always, sometimes, never true, factors, and multiples. So as students are getting ready to think about common denominators, we want to make sure they really understand factors and multiples. And so that's what we're going to look at today. And I generally try to incorporate some statements that'll be pretty easy to put on and some others that require deeper mathematical thinking for them. And then I like to throw in a card or two that would maybe cause a little bit of mathematical discourse for your students. So hopefully you'll see what I mean when I talk about those cards. So with no further ado, let's look at the basics of how this works. So my first card here says multiples of 5 end in 5. So with any kind of always, sometimes, never true activity, what you really want is for students to be thinking about all the counterexamples of that statement, which is how it's getting to those higher or deeper levels of thinking that we want them to have. So in this case, multiples of 5 end in 5. Well, some of them do, 15, 25, 35, etc. But there are multiples of 5 that end in 0 as well. So I'm going to move this card over here to sometimes, because it is sometimes true. And it's not always true, and it's certainly not never true. So the next one, multiples of 2 end in an odd. So again, another pretty easy question or easy statement for kids to figure out, that if they know that multiples of 2 are 2, 4, 6, 8, 10, 12, etc., they're skip counting by 2. And because they're starting with an even number and they're skip counting by an even number, it's always going to end as an even digit. So this one is never true. This one, next card, is a little harder. This is one that, like I mentioned, will require a little deeper mathematical thinking. The difference between a 2-digit number and its reverse is a multiple of 9. So they're going to maybe want a calculator or some scratch paper, and they're going to get to town thinking about this question. And if I just use a simple calculator, I can put a few of those in. So examples like 72. So the reverse of 72 is 27. If I take 27 away from 72, I get 45, which is a multiple of 9. Let's try 91 and take away 19 would be the reverse, and that's 72. Well, 72 is a multiple of 9. How about 58? And that would be 85. So 85 minus 58, that is 27. 27 is a multiple of 9. How about 41 and 14? That's 27. 63 and 36. That's 27. Oh, I'm stuck on 27s. How about 42 and 24. 42 and 24. That is 18. That's a multiple of 9. So in every case that I'm thinking of, I'm getting the answer to be a multiple of 9. So I'm going to make this assumption here that this is true. Now, there are going to be some kids that want to try every single 2-digit number that there is. And that's okay. They can want to try that. But what I would ask students in that case, because you don't want to squash the curiosity mathematically, because when kids are curious about math and want to keep going, I think that's an awesome thing. What I want to do is have them table that idea for a minute, finish the rest of the task for the cards that they have, and then they can come back to that. And maybe that can be their extension, their homework. They want to go home and they want to try to find all of those and, challenge their family, whatever it might be. Certainly, I'm going to let them run with that and see if they can ever disprove this card. But I'm going to move on. So multiples of 6 are 1 more or 1 less than a prime. So if I list out multiples of 6, not counting 6, I'm going to start with the first 5. So if I'm going to go to 12, 18, 24, 30, 36. So 12, the numbers on either side are 11 and 13. Both of those are prime, so that's true. The next multiple is 18. The numbers on either side of 18 are 17 and 19, so that's still true. Those are both prime. 24, the numbers on either side are 25 and 23. So 23 is a prime number, but 25 is not. So in this case, multiples of 6 are 1 more or 1 less. That's not always true, but again, it's not never true because I have examples where it is true. So that goes in the sometimes category. Multiples of 7 are odd. Again, this is a pretty easy one. Multiples of 7 are 14, 21, 28. So there are 49 as an example. So there are times when it is odd. There are times when it is not odd. So I'm going to move it over here. If you add the digits together in a number made up of 2 or more digits, it's a multiple of 3. So this is one where the kids will have to come up with some examples and they'll have to try them out mathematically. So if I add 2 digits together, so if I add the digits 1 and 4 together, for example, in the number 14 or 41, I get the sum of 5. And 5 is not a multiple of 3. So right now I might think this is not true. But I can certainly find instances where it is true. Let me think. 36, 3 and 6 is 9, and 9 is a multiple of 3. So I can find instances where it is true, and I can find instances where it's not true. And when I can do that, that means that it goes in the sometimes category. I also like to throw in some vocabulary for kids to see what they can use in terms of context clues. And if they don't know the word, it's fine. They can look it up. I give kids in the classroom an opportunity to use their resources, use a dictionary, look up a word, use their textbook. I want them using that sucker because, it is good for a few things. So in this case, there are a finite number of multiples of a given number. So kids might not know the word finite. We could talk about the opposite word, which would be infinite, and infinite means never ending. So if infinite is never ending, then finite means there's an end point. There's a terminal point. So is it true or not that there's a limit to the number of multiples that you can have? And that's not true. There is not a finite number of multiples for a given number. So that's a never. Multiples are larger than the original. This is an example where I put in a question that I want kids to be able to argue a little bit about. So if you interpret this question to mean that multiples only consist of the products of the number and other numbers of 2 or greater. So if I'm talking about the original number n times 2 times 3 times 4 times 5, then those are multiples. But some kids will consider, or some adults even will consider, that the number times 1 is also a multiple. And in that case, the answer, the result to a number times 1 is not larger than the original number. And so I might be tempted to say that this is sometimes instead of always. It really depends on how I interpret it. Now, I could also interpret this to say, some kids might say, well, multiples also consist of the products of a number and a negative number, or a number and a fraction. The outcome is still the product of multiplication. And so, but the numbers in those cases, if I take a number times a negative integer, then I'm going to get a smaller product. If I take a number times a fraction that is less than 1, I'm going to get a smaller number as the product. So I'm okay in this case with the answer being sometimes as opposed to always. I think it really depends on your definition of multiple and whether or not you include that product of one, if you allow products of decimal numbers and fraction numbers and negative numbers. What I want students to do is argue successfully their mathematical point. And if they can do it using accurate, appropriate mathematical argument, then I'm going to let them put that card in either one of those categories. So I'm going to just put it here on the line because often, even when I do this activity in workshops, this card ends up on the line. But I say all that because I want you to throw in some statements that cause your kids to have genuine math discourse. And that one does it. How about this one? A square number has an even number of factors. So factors are the numbers that are evenly divisible into the number. So if I pick a square number like 36, the factors of 36, if I create my factor pair list, are 1 and 36, 2 and 18, 3 and 12, 4 and 9, and 6 and 6. And so if I consider that 6 is a repeated factor, I'm only going to count it once. Then I'm going to look at the numbers that I have as factors: 1, 2, 3, 4, 6, 9, 12, 18, and 36. So I get 1, 2, 3, 4, 5, 6, 7, 8, 9. I get 9 factors if I don't count the 6 twice. And I wouldn't because it's the same digit. So in that case, I would say it doesn't have an even number of factors. It has an odd number of factors. So it would not be true in that one case. And if you continue to have that same argument, say I pick 25, well, it has factors of 1, 25, and 5. So that has 3. If I pick other square numbers, you're going to find similarly that they're going to have an odd number of factors. Again, this is one that I'm going to say this is never true, but I might have a student that can successfully argue to me that it's even because they're double counting that squaring number. So it's up to you as the teacher what you decide you're willing to accept and what you're not. And that's the beauty of an activity like this, is that it really not only gets kids thinking about math, but it gets them really arguing passionately about what they believe about math. And you can uncover what student thought is all about. You can uncover a lot of their misconceptions this way, and it gives you an opportunity not only to assess them in a very informal way, but to provide some immediate feedback and then make notes about what you need to cover as a class or with individual students. So it's just such a great activity. It's very versatile, and I hope that you find that you can use the strategy of always, sometimes, never in 100 different ways. You can use it with just about every concept and topic in math. So from here, I would really love to know how you are using it. And so I would beg you to send me an email, and I really want to put something in here so I can show you what my email is. So let me see. I'm going to put in a text box here. Mathematics, if I can spell under pressure. So my name is Kelly, and my email is integralmathematics@gmail, not got.com, but .com. Surely you know what I mean, at gmail.com. And I would love it if you would send me an email with some of your activity ideas, and or comment in the comment line under this video about what topics that you either have already used this strategy with or that you could see it being used with easily. And let's create a community of ideas so that we can all benefit from that as teachers. Thanks so much for listening, and I look forward to talking to you again soon.